screen. I hope all of you can see the screen. And this journal page right now. Right.
Sir,
Yeah, go ahead.
I had a doubt in the proof of second lemma in the last class.
Okay, go
Uh,
ahead.
uh, the proof was like we have to prove that x is zero, x is a multiple of identity, right? And we saw that x prime lambda will be zero only if lambda is an eigenvalue. But what if lambda is not an eigenvalue? In that case, x prime lambda could be.
Yeah, so if lambda is, so the point is what we managed to prove was simply this, that we have this x prime lambda, any number, right?
Yes, sir.
Okay, so lambda could be any number. We are not disputing that. All we are saying is this x prime lambda, of course, obeys this. So ti equals ti x prime lambda, right? Just because x commutes with all the
Yeah.
ti's and lambda identity, of course, commutes with every. So so what does the first lemma tell us about this?
It's
This
either
tells us that
zero or
x prime
invertible.
lambda is zero, or
Invertible.
x prime lambda inverse exists.
Mm.
Okay. Now what we managed to show is that if lambda is an eigenvalue, okay, then x prime lambda inverse of course exists. It does not exist, right?
Yes, sir. But what if lambda is not equal to zero? Then the other possibility can be true, right?
Lambda is not equal to, you mean lambda is not equal to zero, or
Lambda is
lambda is
not
not an
equal to zero.
eigenvalue?
I'm sorry.
If lambda is not an eigenvalue, then x minus lambda this x prime lambda inverse exists, right?
Yeah, exactly. So I mean, the proof, the theorem
So
statement says it
the
has to be.
proof, look, the theorem states that either x prime lambda is zero or x prime lambda inverse exists, right?
Yes, sir.
So if lambda is not an eigenvalue, then x prime lambda is not zero, of course, because then the question of x being equal to lambda it does not even arise, right?
Why?
In general,
Could
sorry, I actually can't really hear you clearly. So could you just slowly say what your objection is again?
no? Could you repeat the last part again? You just you said that from Schur's first lemma, x prime lambda will be zero or it's
Or x
invertible.
prime lambda inverse exists, right?
Yeah.
That's it.
Uh,
So if you choose any arbitrary lambda, the chances are that x prime lambda inverse will exist.
mhm.
And we have nothing to say about that. That's fine. No problem, right? There's no problem with that. All
But
we're saying is that if in particular we choose, now we make a choice. So up to now, lambda could be any number, and now we have up to now we have these two possibilities. Okay, as
yes,
long as you choose lambda to be any number, then these are the two possibilities. And in general, if you just arbitrarily choose a lambda which is not an eigenvalue, then x prime lambda inverse will exist. Not a problem.
but
Okay.
the statement says that x has to be a multiple of identity, right?
Yeah, but then we said okay, fine. Lambda could be any number up to now, but now we have a choice, right? We can choose lambda to be anything. You agree?
So in theory, we can have.
Are you with me so far?
Your
Now what we do is we make a choice.
voice
Yeah,
got cut
sorry.
off. Your
Could you just
voice
repeat
just got
that?
cut off.
Yeah. Is my voice getting okay? Let me just try. Okay, I might leave right now because I may want to change my connection to something else. So I think I'm back. I hope.
Yes, sir.
Okay. So let's see. Let's start the presentation again. Oops. Just hold on. আরে আমি একটু ক্লাসে আছি তোকে ফোন করবি ওকে ফোন করছিলি নাকি ওকে Okay, I'm still connected to you, right?
Yes, sir.
Okay, so as I said, up to this point, lambda could be any number, and this would still be true. Both of these could be true, right? Now I have a choice now to make. I can choose lambda to be anything. I can choose lambda to be an eigenvalue. Every operator x from V to V has an eigenvalue, at least one. May have more, but one eigenvalue definitely exists, right?
I understood how that part comes about. My question was, why do we have to make a choice? Shouldn't the statement hold irrespective of our choice of lambda?
No, that's true. That this statement holds this one and this one. Holds irrespective of your choice of lambda. Okay? But to prove that x is lambda I, look, you cannot, there are hundreds of statements which hold anyway. But when you prove your result, you cannot just disregard all the steps that lead you to the proof and say, okay, fine, that statement was true and therefore, why do I have to go further? Unless you make the choice that lambda is an eigenvalue, then you can't proceed further towards your proof. Okay?
Okay.
That doesn't mean the statement is wrong. That doesn't mean x doesn't become lambda I just because you refuse to choose x to be an eigenvalue. Suppose you chose lambda, instead of lambda you chose mu. Then x prime mu, if I presuppose that I know that x is lambda I, simply becomes lambda minus mu into identity, right? And lambda minus mu is not 0 because I've chosen mu to be different from lambda. So this is invertible.
Oh, okay.
So there is nothing wrong with this statement. There's nothing contradictory here. All we are saying is unless you choose lambda to be an eigenvalue, you cannot proceed to further towards your proof. But when you do a proof, you of course have to carry out a sequence of steps, right? If you don't carry all the steps out, you must check that you're right that you must check that all the steps you have until that point is consistent with what you are going to get. And as I've shown you right now, it is consistent. You choose any other number?
Yes, sir.
Okay, is this correct?
Yes, I got it.
So any further questions from anybody? Okay, so let me just quickly recap where we are right now. We have these results that we have the notion of an irreducible set of operators. I'm not writing down the definition, but operators on a vector space. So that's one notion that is very important. And then from this, using this notion and basically elementary linear algebra, we got to these two things. And just to remind you, this essentially says that if you have two vector spaces v1, v2, and with a map x from v1 to v2, which intertwines between two sets. So I have two irreducible sets of operators, one on the space v1, another on the space v2. And so if you have an intertwining relation, like you first apply x and then apply ti2, that is x carries you from v1 to v2, then you apply ti2. Or you first apply ti1, moving within v1, and then apply x to go to v2. You get the same result for all I. If this happens, then Schur's lemma 1 simply says x equals 0 or x inverse exists. So this is lemma 1. And what lemma 2 says is this, that if xti equals tix for all I, where basically TIs are just a set of irreducible operators on a particular vector space, and X is a map from V to V. Just hold on. Hello? Yes? बात देखे? हाँ हाँ हाँ. The problem is I'm in a class right now, and you want an attestation, right? You want an attestation. এটা আমার কোনো আইডিয়া নেই প্রথমত I am not I cannot do the attestation. My wife can, because my wife is a official member, but my wife is actually in college right now, and I don't know whether আগে তো মনে হয় if it's a legal issue then education service লোক দিয়ে হয় না, you have to get it notified, notarized. আমার যতদূর no আজকে she will return today at around 2 o'clock. You call me, then I will get up. Okay. Sorry for that. Sorry about that. So we have this xti is tix for all I, and then we get that x must be lambda. This is exactly the result we were talking about. This implies that x must be a multiple of the identity, which of course includes 0, right? So this is where we are. So once we are sure about this, let's go on to the next topic, which is some applications of this Schur's lemma. So application number 1 which we are going to talk about is actually quite an important result, but it's a very simple result, which is all irreducible representations what that means simply is that if you have an irreducible representation of G, an abelian group, on a finite dimensional vector space, then that vector space has to be 1D. You can't have it on have this on a more than 1D space. Okay, I hope everybody is still with me. So how do you prove this? The proof is simply by contradiction. Assume has an irrep which on a space V with dimension of V greater than 1. And we will show that this leads to a contradiction. Okay, you must keep on responding from time to time, otherwise I'm not very sure whether I'm still with you. Now it seems that I'm not with you.
No, sir.
Okay, yeah, I am.
No, sir, you are.
Okay, fine. So how do you do that? The idea is, so irrep, let's call that irrep L. So since for all G and G prime belonging to capital G, we have GG prime equals G prime G. We have LG prime, which is LGG prime. That's LG prime G, so it has to be LG prime LG for all G prime belonging to G. Okay, so now let's just take a look at this. If the set LG prime right. So this is important because this is exactly why we are at all interested in this irreducible set of operators in the first place, right? If you have an irreducible representation of a group, then the operators corresponding to the representation always form an irreducible set of operators on the representation space, irrespective of whether the group is abelian or not. This statement is true for all irreducible representations. But now you take a look at this. What is this telling you? It's telling you that the operator LG commutes with LG prime for all G prime, right? So if you focus on a particular G, LG commutes with all the LG prime. So what do you have? What does this tell you? Q's lemma 2 will immediately tell you something about LG. What will it be?
Identity.
No, not identity, but a multiple of the identity, right? LG, that's what Schur's lemma 2 tells you. Any operator which commutes with every one of a set of irreducible operators has to be a multiple of the identity. So LG has to be lambda I. But is this true only for, and lambda of course could very well depend on G. But is this true for a specific G? Of course not. This works for all the G's, right? For all G belonging to capital G. Okay? Is this okay with everybody? I'm waiting for a response because I'm not sure whether I'm getting through.
Yes.
Okay, and this simply means that any 1D subspace of V spanned by right? With all the lambda G's, LG's are multiples of identity. Take any vector V, take any one vector with small v belonging to capital V, okay? And apply all the LG's on that. What will you get? You'll get something in the same direction, right? You'll get something which is V times a number. Which means that the 1D subspace which is all multiples of V for a given non-zero V is invariant not only under LG, it's actually invariant under all the LGs. Is that okay?
Yes, sir.
And that's a contradiction. Can you see why? Why is this a contradiction? There's a contradiction between this statement here and this statement here. These two contradict each other. Can you see why? The top statement says that because L is an irrep, if you take all the LGs together, LG prime for G prime belonging to G is of course the same set as LG for G belonging to capital G. If you take all the LGs together, they form a set of irreducible set of operators on V. And what does it mean? That means that the only subspace of V which is invariant under all the LGs is either the trivial space, null vector alone, or the full space, right? Now we have assumed that V has a dimension more than one, which means this subspace that we have found out right now, in fact we have found infinitely many of them, but we don't need infinitely many of them for the contradiction, we just need one of them. What we have done is we have found out one vector space, the space spanned by small v, which is invariant under all the LGs. And that is impossible because it goes against the definition of what an irreducible set of operators is. Is that okay? Yes? No?
Yes.
If there is a no, please tell me. And since this is a contradiction. Contradiction with what? We started out by the assumption that capital G has a irreducible representation on a vector space of dimensionality more than 1. Right? And we get a contradiction because then we will be able to find a non-trivial subspace which actually what do we call it? Which is actually invariant under all the LGs, which means that you cannot have an irreducible set of operators. Is that clear? So the proof essentially goes this way. You start with the assumption that there is an irrep on a space V with dimension more than 1, and you show that if that is true, and if there is irreducible, which you're assuming, but because that's why you can use Schur's lemma too. You end up with the statement that LG is multiple of identity for all the G's, and that means every vector space spanned by a single vector is invariant. And so unless dim V is exactly equal to 1, and that is the entire vector space, you are in trouble because you get a contradiction between what you started with and what you have arrived at. Okay. So because of this contradiction, you can say that, okay, this assumption that we made that dim V is more than 1 cannot be right. So which means that dim V, for all irreps, dim V is just 1. You can't have more an irreducible representation of an Abelian group on a vector space which is more than 1 dimension. Doesn't mean that you cannot have a representation. You can of course have a representation. What you can't have is an irreducible representation. Okay? So if that is clear, we will move on to the next topic. So before we do that, if it's not clear, just speak up. If not, I'm going to move on to application 2, which is actually the more important application for us, which essentially is the statement of orthogonality in matrix representations. So although we proved the two lemmas and stated and proved both the lemmas in operator language, not in matrix language, simply because the proof was easier in operator language, it's pretty easy to see that you can actually translate that trivially to the matrix language, right? So instead of an irreducible set of operators, you have an irreducible set of matrices. Instead of this operator which takes you from one vector space to another vector space, you get a matrix which is perhaps a rectangular matrix, so the two dimensionalities are different and so on. Is that okay? So let's set up the premise of this application. That is, not R, that's bad English. Of course, remember when you say irreducible matrix representations, you mean representations which cannot be brought to the block diagonal form by a similarity transformation, right? Which is equivalent to have the original operators which they represent being irreducible set of operators. Of a, oops. finite group. So all I'm saying right now will work for finite groups. The extension to compact groups, which we will talk about later, is sort of trivial, and this does not really extend that well to other kind of groups, and that's why, since the orthogonality relations are actually very, very useful, non-compact groups are actually quite difficult to deal with. And we try to avoid them as much as possible, except that sometimes they're so important that we cannot avoid them. So the general method results that we have for compact groups and finite groups, actually these are results for finite groups which can be extended to compact groups. Those general results don't work for non-compact groups. So non-compact groups require special treatment. Okay, so that's one thing which you have to be borne in mind. For the time being, all we are saying is about finite groups, so this is not an issue right now. Now I make a restriction here. With the two irreducible representations, but I make a restriction that they are which are either identical, which means d alpha and d beta are the same representations, not equivalent ones, same. That means they have the same matrices for every G, or inequivalent. Okay. So I'm just saying that if two matrices are equivalent, two representations are equivalent, we are not going to talk about them right now. All we are saying is I have two representations. They could be the same representation, that is d alpha and d beta may be exactly the same. If not, they are inequivalent by the supposition right now. Okay. Then, of course, d alpha could be an m-dimensional representation, d beta could be n-dimensional in general. And of course, if they are identical, then m and n would of course be the same. Now, what we do is we consider a special matrix M, which is defined this way. So I'm pretty sure all of you will realize that this is very, very similar to the unitarity, to this proof that we had of every representation being equivalent to an unitary representation. We started there with something which is very similar to this, a sum over the entire group. Just to point out, this is m by m. Let me just use a different color for this. This is m by m. This is n by n. And this Z must then be an m by n matrix. Now, which m by n matrix are we talking about? The answer is it could be any m by n matrix right now. Okay. So this m here, the capital M on the left hand side, is really not one matrix. It could be any one of the infinitely many possible matrices you get by changing Z. Or if you're just interested in independent ones, which you would be, there are mn independent matrices possible, right, for Z. Well, every m by n matrix can be written down as a linear combination of the mm elementary matrices. When I say elementary, I mean only one element is 1, everything else is 0. If you start with a matrix like that, a bunch of matrices like that, that of course very small m times small n in number, then any m by n matrix can be made up as a linear combination of them. So I actually don't really have an infinitely large number of matrices capital M, although it looks like that. For all practical purposes, I do have m times n independent matrices capital M to talk about. So this is okay with everybody. So although I'm saying consider a or an, actually an m, in English that's what you are supposed to say, because m starts with the a sound. This is really not an, it's really a bunch of. Okay. For the timing, let's focus on any one of them. So I've chosen a specific Z, I've got a specific M. Okay. Why am I looking at this? That will be clear soon. Now, why I'm looking at this is simply this. Let's try out and find what this is going to be. This, of course, is going to be d alpha g sum over all g prime d alpha g prime So you're with me so far, right? So this is sum over g prime belonging to capital G. Now I just move the d alpha g and d beta g inverse inside the sum. This is where the sum being finite, that is the group being finite, becomes very important, right? The sum is over a finite number of terms. So I can just move the d alpha g in from the left, d beta g inverse in from the right, and then sum up. This is exactly why finiteness and later for infinite groups compactness becomes important. This step is what fails for non-compact groups in general. So what we get is d alpha g prime, which is just d alpha g prime, z, and d beta. D beta will have an argument g prime inverse g inverse. I'm using the fact, of course, that there are representations. And then just, and so this is the same as M. Okay, any doubts about this?
No, sir.
Okay, fine. So let's see what this means. It means that I have found a bunch of matrices M which actually commute, or actually not commute, but intertwine between all these matrices. So what do you know about M?
Multiple of
No,
identity.
no. We are not yet at the Schur's lemma 2 level. Not yet.
0 or invertible.
A 0 or invertible, that's right. Okay? So this is really Schur's lemma 1 right now. So
Oh, because beta is there's alpha two
there are two
representations.
representations involved. They are not.
Because
We have not assumed that they are identical yet, or they could be, but in general, M equals 0 or M inverse exists. Now let's take this in two steps. If M inverse exists, what is that telling you about d alpha and d beta?
They're equivalent.
Yeah, but is that possible?
Contradictions.
Not really. It's not really a contradiction, but a contradiction would be something which is impossible. But the second possibility exists or is achievable, let's put it that way, only when, remember what were our assumptions? That d alpha and d beta are either inequivalent or
Identical.
are identical. Okay? So if M inverse exists, then they're equivalent. You're right. But the only way that can be possible is achievable only if alpha equals beta, because I've deliberately chosen these to be inequivalent or identical. So unless alpha is equal to beta, you are going to get a 0. Is that okay? Notice that this is exactly why I have decided to make this restriction. I am going to not count equivalent representations as distinct representations. So what am I really doing here? I'm starting with the group G, I'm taking all its irreps. At this stage, I don't even know whether the irreps are finite or infinite in number. It will turn out to be finite in number for finite groups very soon. But right now, we don't know any of that. Is that okay? All we know is that there are some irreps. So what I do is I collect all the irreps together. Perhaps I label them D1, D2, D3. But what I do specifically is that if two irreps are equivalent, I don't count them both. I only take one of them. So I have this sequence of irreps which I've built up, some arbitrary sequence. You could say they could be ordered by dimension, but you could have more than one irrep of a particular dimension. So this is essentially an arbitrary ordering. I just order the irreps in some way, taking care not to choose equivalent irreps twice. I choose only one of them. Okay? Because I've done that, then unless alpha is equal to beta, the second possibility that M inverse exists cannot be correct. That means if alpha is not equal to beta, this M must be 0. So what does that tell you? It tells you first of all, M must have a delta alpha beta factor. If alpha and beta are different, it has to be 0. But if alpha and beta are identical, then comes Schur's lemma 2. If alpha and beta are identical, you are saying M is a matrix which commutes with all the d alphas, right? Is it okay? And then what does it tell you about M?
Now it's a multiple of identity.
Now it has to be a multiple of identity. So it's either 0 or a multiple of the identity. And of course, this lambda would depend on the matrix M that we are talking about. Or, to be more precise, it will depend on the matrix Z, because the matrix M is really dependent on the matrix Z, right? Is that okay? So this is just a compact way of writing both the things together. If alpha is not equal to beta, M is 0. If alpha is equal to beta, M is a multiple of the identity. With what multiple? That of course depends on the specific M. Okay? And the specific M is only dictated by the specific Z you have chosen. Everything else in the thing is already given, right? This group G has some specific representation that you have chosen. All the d alpha G's are given. Is it okay now? So this is something which is critical for the rest of our work today. So is everybody sure about this step? So SL1 says if alpha is not equal to beta, M is 0. And if alpha is equal to beta, then SL1 says fine, M does not have to be 0. But then SL2 says M has to be a multiple of the identity. Put them together, you get this. Clear with everybody?
Yes, sir.
Okay, fine. So now, so M, which remember is sum over G belonging to G, D alpha G, matrix Z, D beta G inverse is some number which depends on Z, delta alpha beta times the identity. Okay, which identity are we talking about? This is of course the identity matrix. So is this the M by M identity or an N by N identity?
Alpha equals to beta, so M.
So it doesn't matter.
M
So it
by
doesn't
N.
matter, right? Because alpha
M
is equal to beta, so M and N have to be equal. Otherwise, delta alpha beta makes it 0 anyway, right? So that's the basic philosophy of writing something like this. I don't really care what other things are multiplied this with when alpha is not equal to beta, because delta alpha beta will make the expression 0 anyway. So now the job is find out lambda Z. And okay, what is the easiest way of finding out lambda Z? And if you're saying M and N, let's say small d alpha, small d beta for dimensions. So d alpha is what we were calling M. d beta is what we were calling n. So now I want to find out lambda z easily. How do I do that? This is actually crying out for something. You should be able to immediately tell me what to do. Remember, this is a matrix relationship, right? D alpha, d beta, z, these are all matrices. Everything here in this expression are matrices. And you want to find out one single term lambda z from this. So what can you do so that the right hand side gives you just lambda z? Or at least tells you how to find lambda z. Of course, the first thing you do is choose alpha equal to beta, right? Don't bother about alpha not equal to beta because that will not tell you anything about lambda z. So you get lambda z I is sum over all small g belonging to capital G, d alpha g z, and now z has to be a square matrix, right? Now d beta is d alpha So now what do you do to find out lambda z? If you have an expression like this, what is the easiest way of simplifying? What can you do to a matrix like this so that the result becomes very simple? Come on, if you forget the sum for the time being.
Sir, I have a
Go ahead.
question. Does lambda not depend on the representation we are using, I mean on alpha?
Yeah, it does. But representations are fixed anyway. So we have already chosen some irreps. And we will find that it will not depend on that. So that's why I didn't bother even writing alpha as in the notation. But anyway, you could just say that we have chosen some fixed irreps anyway to begin with. So that dependence is anyway fixed from the beginning. All I'm saying, once I fix the irreps, there are z's which I can choose arbitrarily, and lambda now will of course depend on the z. And as we will soon see, it does not depend on the irrep, except in one very simple detail, and we will be able to show right now. If you can tell me how to find out lambda z, the answer will be sort of trivial. So if you did not have the sum,
I mean, what if you write identity as 1 by n of summation d alpha g inverse?
I can. Then how does that help?
Then I can take the left hand side.
Okay, so right. So you get z minus lambda z I identity. So you get something rather complicated. Instead of z here, you get z minus lambda z I.
Yeah, that the new m would be 0. So
yeah, so this will be 0.
So can we conclude that z minus lambda I is 0?
No, because it's part of a whole sum. If you did not have the sum, then you could say z is lambda z I. But that would be disastrous, right? Because that would be absurd. Because z is in your hands. You don't have to choose z to be a diagonal matrix. If you did not have the sum over G and this still were correct, then you would end up saying that d alpha G is z minus lambda z I, d alpha G inverse is 0, which of course means z minus lambda z I would have to be 0 and z would have to be lambda z I. But that would go against your free will, right? You could choose z to be anything, any environment matrix. And what rescues you from that lack of free will or that imposition that your free will does not exist so that you cannot choose your z is that this works only if this basic thing only works for the sum, right? Not for individual terms. But I would like to point out that this is really very, very simple.
We can just take the trace of both sides because things cyclically commute inside trace.
Okay, good. But why not determinant? Determinant also would sort of look. This is okay. You're right in the sense that first hint would be this thing is a similarity transformation, right? This is for a given alpha. Of course, what I did not, what I did take for granted that everybody understands is this, that this matrix of course is also the inverse of d alpha g, right? Is it okay with everybody? We have already used it several times in getting here. So this is a similarity transformation. The Z gets similarity transformed by d alpha g, but the only problem is summing them all up for all the g's. Because it's similarity transformation, the two things that you always look for when you're doing a similarity transformation are the two simple results that you have. The trace does not change when you do a similarity transformation, and the determinant does not change. So these are the two obvious things you would always look for whenever you have a similarity transformation. So, as you rightly said, you should take the trace. Why not the determinant?
Because trace is linear, determinant is not
Exactly.
linear.
Exactly. There's a sum, right? So you don't have any clue about how to find the determinant of sum of matrices. But the trace of a sum is trivial. The trace of a sum is simply so you take traces of both sides. So what you get on the right? On the right, what you get is sum over all g belonging to capital G, trace of all of these. But what is the trace of any one of these? It's just the trace of Z. Right? And what do you get on the left hand side? Lambda Z, do you get lambda Z or you get something else?
Dimension of the representation.
Yeah, you get lambda Z times d alpha. Right? So as I said, there is only one small way in which the dimension, the irrep that you are looking at actually comes in. In this formula, you can easily see lambda Z. There is no trace. Sorry, why did I just write it there? There is no sign of the representation except in this one thing, the dimensionality. So what is lambda Z coming out to be? It's coming out to be 1 by d alpha, 1 by the dimensionality of the representation, mod g meaning number of elements here, because that's what this is going to be, times trace of Z. Clear? Okay, when I say clear that loudly, it might even end up being proof by intimidation. So I hope everybody did understand why lambda Z is this.
Yes.
Okay, so what did we end up with? Ultimately, we ended up with this result. If you take any arbitrary, in general, rectangular matrix Z and form this sum, the result is going to be mod g by d alpha trace of Z delta alpha beta. Okay. Now you might say, if it's a rectangular matrix, what does trace mean? But you would realize that I don't care, because if it's a rectangular matrix, that means alpha and beta are different. So delta alpha beta is 0 anyway, so I don't even care. Okay. So the right hand side, of course, the factors in the right hand side only make sense. The factor other than the delta alpha beta only make sense or make unique sense when you're talking about a square matrix, but that's fine, because when alpha is equal to beta, that's what you're going to get. Clear? Everyone? So this is the basic orthogonality relation, or this is actually also called GOT, not the Game of Thrones, of course, but the Great Orthogonality. Oh, where did the T come from? That seems to be Freudian. Oh, theorem, right? T is theorem, not throne. So, Great Orthogonality Theorem, essentially one form of that is just this statement. So, if everybody is with me, we are now going to go on to look for specific applications of that. Everybody is with me so far?
Yes, sir.
Okay, now we notice that we could have chosen Z to be anything, right? Not anything has to be an M by N matrix, but apart from that, anything. D alpha by D beta matrix. Now that I'm using small d alpha, small d beta as a language. Okay, so now if I wrote this thing in, yeah. Oh, sorry, I missed out the identity here.
Sir,
Yeah, go ahead.
sir, uh, in the um, in the statement, it said that either identical or inequivalent.
Right.
So mm, we saw that it's either how are we seeing that it's inequivalent? Is it because of the delta alpha beta?
No, we are saying, look, that was a long time ago actually. When we, let's go back a bit. We proved that M is either 0 or M inverse exists, right?
Yes, yes.
So what we said was, if M inverse exists, when can that happen? Because we have made a choice, right? This is really how we chose to label our representations. We have a bunch of irreps for a particular group G. We do know irreps exist, okay? But once we have a bunch of irreps for our group G, we will not necessarily list all of them. We will just go by, if I've already listed one irrep, any irrep equivalent to that, any irrep you can get just by doing a similarity transformation of all the matrices, I will just not count that. Okay, so that's not even labeled, that's not even counted. Okay, that is my setup. That's how I set up the D alphas. And that this exists, that this implies that M inverse can only exist if alpha and beta are the same. Otherwise, what would have happened? If M inverse existed and alpha and beta were the same, or were not the same, then D alpha and D beta would end up being equivalent representations which are not identical, which is not allowed by our premise. Okay? So then, if that is ruled out, then the only other possibility is M has to be 0, which is why you are saying delta alpha beta. Okay, so I've just made this as a simplifying assumption to begin with, assumption about my set of irreps. I'm simply not going to count equivalent irreps as distinct elements in my set of irreps. Okay, so when we say, ultimately we will end up by saying something like the number of irreps a particular finite group has is just equal to the number of its classes, which of course is absurd. The number of irreps a particular group has in general would be infinite. When I say number of irreps, I mean number of inequivalent irreps. Equivalent irreps will simply not be counted as different irreps. Just hold on, I will answer the door. Thank you. Okay, so I'm back. Any further questions in the meantime? Did I complete what I was saying? I have even forgotten that.
Sorry, it's clear.
Okay, now that we have this, of course, I missed out the identity at the end when we wrote that last time. So let's write it out properly. All the rest, these are just bunch of numbers, right? And this is what makes it a matrix. Okay, now we can of course look at the elements of this. So sorry. So k prime going from 1 to infinity, L prime going from 1 to d, sorry, 1 to d alpha, L prime going from 1 to d beta. This is d alpha g k prime z k prime L d beta g inverse L prime L. Right? This is the kth element of the matrix on the left. D alpha.
So there should be additional summation over G on
some over, of course, some over G. That is critical. That of course was always there, but I forgot to put that in right this time. Trace of Z, delta alpha beta, and what happens with the identity on this side? This is an element, right? It has to be a number on this side. So what number do I put in here? Yes?
delta
KL, because it's nothing but the KLth element of the left hand side, so it's a KLth element of the right hand side as well. So identity's KLth element is just delta KL. Now comes the fact that this is true for all Z, right? I can choose Z to be anything I want. In particular, I could choose Z to be such that say K prime Z has only one non-zero element. Okay? Let's say at the K prime L prime position. Of course, that is contradictory to what I wrote down a while ago, because what I wrote down there, K prime and L prime are not specific positions, they're dummy variables of summation. But let's just say, I can of course be more precise about this. Let's say I could say Z K prime L prime, or Z K double prime L double prime. The K double prime L double prime element of Z KL is delta K prime K double prime delta L prime L double prime. That means there's only one element which is 1, every other element is 0, and that non-zero element is sitting in the K prime L prime position of the matrix. Okay? And then what will the right hand side become then? First of all, that's the easy one. Mod G of course has nothing to do with what Z you've chosen, neither does delta alpha. Delta alpha beta delta KL, these have nothing to do with the Z. So what is the trace of Z now? So this is single one in the K primeth row and L primeth column. So what can you say about the trace? Yes? The rest of the elements are all 0. So what's the trace of such a matrix? In case you're wondering about what happened to my objection about the dummy index, let's just make all these double brackets, which I can always do, right? I can always change the dummy index or summation to anything I want. So what's the trace here? This trace of Z. Come on, I thought that was the easiest part.
So d alpha, right? I'm slightly confused with the indices.
So
Should
which indices
be
are you confused about?
delta k prime L prime.
Right. So can you explain that to so that the confusion goes away?
I mean,
right.
it's the only place where the one is now. For the trace to be there, k prime has to be equal to L prime. Otherwise, the trace is 0.
Right. So if k prime is not equal to L prime, the only one is outside the diagonal. Then every element of the diagonal
Exactly.
is 0. So the trace is 0. And if k prime is equal to L prime, then we are talking about a matrix which has only a single one somewhere on the diagonal. All the other elements are 0. So trace is going to be 1. Is this clear? The square matrix ends up looking something like this: zeros, bunch of zeros, all zeros, everywhere zeros, a one sitting somewhere. If that one happens to be in the, say in this case, I have just lost count of how many I wrote. Anyway, if that one happens to be, in this case, on the third row and the third column, so it's on the diagonal, so trace is 1. If the one happened to be on the second row, third column, then it would be off diagonal, right? And that would mean that it will not contribute to the trace. Is this okay?
Yeah.
I've just chosen a very specific Z, which makes the trace calculation trivial. It also makes this whole messy sum out here rather simple. Because ultimately on the left hand side all you get is sum over all G d alpha G kk prime d beta G inverse. Okay, this is getting too messy, so let me just move on and write it on the next page. The equation we have, it's really sum over all G belonging to capital G. D alpha, take the D alpha matrix corresponding to G. Take its k prime element. This is now is a statement about a single specific element, by the way. The k prime element. D beta G inverse. Take the, I think I've in too many brackets. D beta G inverse L prime Lth element equals mod G by D alpha delta alpha beta delta KL delta K prime L prime. Now, do you realize how many equations we have here? So, for a specific pair of representations alpha and beta, okay, let's choose alpha, let's fix it, let's fix beta. Once you have done that, how many equations are we talking about which has been written down right now? How many distinct equations?
Dimension of the representation squared.
Well, actually, it's not that. It's dimension of the representation alpha squared times dimension of the representation beta squared. right? So if we have a three-dimensional, a four-dimensional representation, there's really 9 times 16, 144 different equations that we are talking about here, right? Remember, k takes any one of the d alpha values, k prime takes any one of the d alpha values, L prime and L each take any one of the d beta values, and there is no sum over any of k, k prime, L prime. Each one of them are free indices, right?
Yes, yes.
So this is a huge number of restrictions which you are imposing on irreps. You are not imposing them, they are coming out automatically, but all this is telling you that being an irrep is not very easy. If you have a matrix representation which is irreducible, it puts a huge amount of strain on the individual matrices. There are a lot of constraints to obey. Very many actually. Okay? Yeah. So it's no wonder that the irreps sort of can be almost completely identified just from this set of relations. It's not one. The important thing is, although we call it a orthogonality theorem, it's not really a single orthogonality theorem. And maybe that's why the great word is used in front of that. It's really many, many results rolled into one. A huge number of restrictions which are imposed on the irrep automatically as a consequence of Schur's lemmas. So no wonder a lot of information can be extracted about the irreps simply from these. You don't have to even go very far from here. Sometimes you don't even have to construct the irreps explicitly in order to find out most of the results. Sometimes you will find almost everything from the GOT, and then maybe not everything can be found from the GOT. You may have to consider one or two irreps explicitly, but that's it. This cuts down the job a lot simply because it's saying a lot of stuff. I want you to appreciate that. It's not, we call it a theorem, but it's not one theorem. That's one thing which you have to bear in mind. Is this clear now? Why this is such a, why is this great? Why the word great is there in the name? Okay, that was, okay, I didn't expect a response to that anyway, but I hope you appreciate that this is not one relation, it's a bunch of relations. And in particular, for unitary representations, so far these are statements about any representations. For unitary representations, you actually go a bit further, simply because these are, of course, statements about d alpha g and d alpha g specific elements times d beta g inverse specific elements. If it's a unitary representation, then what is d beta g inverse for a unitary representation? Yes?
Dagger, right?
Yeah, it's a dagger of d beta g. That's a Hermitian adjoint, or whatever you call it, the matrices of d beta g, right? So it's d beta g daggers L prime L element, or d beta g is L prime element conjugate. Just remember the ordering. Here you have L prime L, here you have L prime. And this, of course, the right hand side, of course, doesn't care what you are, what kind of representation you're talking about. It's going to delta k L, delta k prime L prime. Okay? So this is for all, this is for any representation. Of course, with the additional restriction that these are all irreps and which are either identical or inequivalent. But you specialize to only unitary representations, and remember you can, right? Because we already have a theorem which says that all representations, forget irreducible representations, all representations of a finite group are equivalent to a unitary representation. So all these irreps are also equivalent to a unitary representation. So what I could have done at the very beginning is that I could have made this restriction that when I'm going to count the irreps and label them, I'm only going to take a unitary irrep. So if the irrep which I found is not unitary, I will just carry out the procedure that we talked about there, change it into an unitary irrep, and just take that. Well, I don't have to do it, but I can. And the very fact that I can is enough for many of the interesting results that we are going to get. So you're with me so far?
Yes.
Yeah. Any questions? If not, let's move on to the last topic of the day, which is this is actually great that you have a lot of information here. As I said, huge number of equations all rolled up into one. But sometimes the problem is it has too much information. You can actually cut down on the information and still get enough to be useful. If you have way too much, then it becomes a question of not being able to see the wood for the trees. So what you do is, instead of looking at the entire irrep, you look at something much simpler or much smaller. And well, this again is defined not only for irrep but for any representation. So if you have a matrix representation, of course this works not only for matrix representations but also operator representations, because once you have an operator representation, you can always choose a basis and get a matrix representation, and then you can define for a matrix representation d alpha, and define this. Okay, take the matrix representation. That means you have a matrix for every one of your group elements. You take the trace of every one of those group elements. That's just a number, and you assign that to a function. This is a function which maps the group elements to a number. Okay, that clear? And I said a while ago that this is actually something you can do even at the operator level. So I hope everybody is sure about why we can do this at the operator level itself. So I can define a character of a representation even if it's an operator representation, not a matrix representation. Everybody is sure about the steps involved? Suppose somebody gave you an operator representation on a vector space. How would you define the character of that representation? Somebody tell me, how would you do that?
We'll choose any basis and take the trace in that representation.
Right. You choose any basis on your vector space that gives you a matrix representation, and you take the trace of that particular matrix representation. Okay. And of course, everybody should be clear about that. This works because it does not matter which basis you choose, because if you were to choose a different basis, the new matrix representation, which will be different by the way from the one you have got, will be formed out of similar matrices compared to the original matrix representation, and that means the character or the trace will stay the same, right? Okay. So chi, or chi alpha to be more precise, chi alpha of G is just a number. Chi alpha is the character map. It's a function on the group G which returns numbers, real or complex depending on what kind of vector space you have. Chi alpha this is going to be important for us soon, is what is called a class function. What that means is the value of chi alpha does not depend really on the group element so much, but on the class to which the group element belongs. Everybody remembers what a class is in the context of a group? Yes? No? What?
No, sir.
Okay, so this basically has nothing to do with representation theory. This is one of the topics in abstract group theory which I did not mention, assuming that people would remember. But let's say two elements G, G prime belonging to G. Remember what conjugate means in the language of group theory? Each other if some, let's call it H belonging to capital G, such that G prime is HG H inverse. Everybody remembers this, right? Yes?
Equivalent classes, right?
Yeah, but this is okay, this is conjugacy, this is the conjugacy relationship. Then you show that this thing to be conjugate to is an equivalence relation. Right? That's easy to show. Is conjugate to is a relation. And not only is it a relation, it's an equivalence relation. That is to say, symmetric, transitive, and reflexive. Reflexive is obvious because, okay, why is it obvious? The G is always conjugate to G. Okay, let's have the proof that that conjugate this is conjugate to is an equivalence relation. What's the proof of that? Come on, quickly. How do you prove it's reflexive? Everybody remembers what an equivalence relation is, right? It's a relation which is reflexive, symmetric, and transitive. Reflexive means every element has to be related to itself. So how do you show that G is conjugate to G?
Using identity.
Yeah, you have to just show one H which will do the job. Just use identity. G is EG E inverse. Done. And G is also GGG inverse, right? So you don't have this H does not have to be unique, but it has to exist. Similarly, symmetric is trivial because if G prime is conjugate to G through H, it's obvious that G is conjugate to G prime through H inverse. And this being a group, every element does have an inverse. And similarly, if G is similar to G prime, G is conjugate to G prime is conjugate to G double prime, then you can easily show that G is conjugate to G double prime. So this is an equivalence relation. And because this is an equivalence relation, can define equivalence classes. So this is by definition all G prime such that exists H belonging to G so that HG H inverse, sorry. So you collect all the inequivalent, all the conjugate elements together in a group, you get a class. Okay, clear? And because there is a general property of every equivalence relation, equivalence classes partition a set, which means the entire group can be partitioned into classes. We have already seen another kind of partitioning of a group. That partitioning was in terms of the cosets, right? Is in the same coset for a given subgroup of a group, is in the same coset is an equivalence relation, something we proved, and hence being in, if you take the cosets, they're actually just equivalence classes under that particular equivalence relation, and so the cosets partition the group. Now the cosets of course are all exactly the same size, the size of the subgroup, which is what gave us Lagrange's theorem, right? That the order of a group is divisible by the order of a subgroup for every finite group. But here we have a different kind of partitioning. Elements which are in the same conjugacy class belongs together. So basically that's what you call a conjugacy class. Elements which are conjugate together, put them together. So for example, with our example group that we had, the S3 group, remember E, A, B, C, D, F, the conjugacy classes here is this. Identity is always in a conjugacy class by itself in every group, right? Because the only element which can be conjugate to the identity is the identity itself, right? Nothing else. Is that okay? I'm assuming it's okay with everybody. The other conjugacy class happens to be the three rotations together, and this one is, there are three conjugacy classes. I will urge you to check using the multiplication rule. Either you have already finished up the multiplication table. If you haven't, work it out and then show that these are the three conjugacy classes for the group S3, the example that we had. Okay with you, all of you so far? Of course, this can be something which you can show only after working it out, but I hope you have figured out how to work this out.
Yes,
If there is okay, I hope there's no doubt about that. And by the way, the reason why I could say ABC is in a conjugacy class and DF is in a conjugacy class, I didn't really work out the entire multiplication table here. It is not in my head. I'm not that good. But there are certain obvious geometric properties which can use to show that ABC will have to be in a conjugacy class. I will just let you figure out what the geometry is here. Remember, ABC are reflections and D and F are rotations. It's not true that all reflections have to belong to the same conjugacy class or all the rotations have to belong to the same conjugacy class. But there are some ways of figuring out what the conjugacy classes will be, and geometrical ways. Just think of what these reflections and rotations actually do. And that's what I used to write down the conjugacy classes. Right? Yeah, go ahead.
It's like because of the parity, reflection flips the parity. Not exactly parity, in a loose sense.
Okay, but every reflection does that, right? But that does not mean that if you have a group with a bunch of reflections, all of them will have to belong to the same class. Here it happens, but that's because of something else. Similarly, it's not true that all rotations belong to the same class. They don't in general.
Mm-hmm.
For example, in a square, say the symmetric group of a square, you will have four rotations, right? 0 degree. Here, of course, you can see even in here you can see all rotations don't belong to the same class. There's one rotation, the identity, which is of course a 0 degree rotation, does not belong to the same class as D and F. So for a square, there would be four rotations, right? 0 degrees, 90 degrees, 180 degrees, 270 degrees. And there, in the symmetric group of a square, you will find the identity again sitting in its own class, the 180 degree rotation sitting in its own class, and the 90 degree and 270 degree rotations sitting together in their own class. So I will urge you to think about the geometry involved here, and just thinking about the rotations won't do. You have to think of the whole group, because remember, this H that you are using to conjugate G with G prime could be any group element. If you are talking about the symmetric group of an equilateral triangle or a square, you are essentially talking about only rotations and reflections. So to just pay attention to what they do geometrically. But okay, this was of course an aside. This is something which we should have discussed maybe in the preliminary talk part. But can you now see why chi alpha is a class function? If a class function meaning every element which belongs to the same class, every group element which belongs to the same conjugacy class has the same character. Why? Because chi alpha G prime, where if G prime is in the same class as G, then chi alpha G prime will be trace of D alpha G prime, but G prime is H, G, H inverse, right? But then you use the fact that this is a representation, so D alpha of H, G, H inverse is D alpha of H times D alpha of G times D alpha of H inverse, which is D alpha of H inverse, and then use the fact that trace is cyclic and show that that's the same as D alpha G. Okay. So the number of different values which a class can take, which character can take, actually is the number of classes of a group, not the number of elements. Despite the fact that chi alpha G is a function of G, the number of distinct values it can take at most is the number of classes. And I will submit to you that that actually is a very important result. That's going to be very important soon. Okay, clear? Okay, let's quickly move on to what does the Great Orthogonality Theorem actually tell us about characters. So just to remind you, this is what the Great Orthogonality Theorem told us. You take sum of G, D alpha, G, K, K prime, D beta G inverse, L prime L. We are talking of general representations now, not necessarily only orthogonal ones, or not necessarily only unitary ones. And that was the dimension of the group divided by the size of the representation, and then a bunch of delta symbols, delta alpha beta, delta K L, delta K prime L. Okay. Now, if I want to convert this to a statement about traces, what do I have to do? All I have to do is how do you get a trace here? All you have to do is set K equal to K prime, sum over all K, right? And what do you have to do here? Put L equal to L prime, sum over all L. Is that okay? This, remember, is valid for all K prime, all L prime. So I can of course choose K prime to be the same as K. So that will just give me a diagonal element, but then I can sum up over the diagonal element. And of course I have to do it on both sides. So what is the left hand side coming to be if you do that? So this is the prescription, put K equals L and K equal to K, not put K equal to L, sort of assuming the answer. K equal to K prime and L equal to L prime. Okay, when I say this, I'm really saying the wrong thing. I should say K prime equal to K and L prime equal to L. Make choice about them. Then I have K and L as the only indices left. And sum over K and L. Of course, I do it to both sides of the equation. So what do I get on the left hand side? Help me out here. What do I get on the left hand side?
K equal to L.
No, on the left hand side. This side. If I put K equal to K prime and sum up over all K. Okay, I put K prime equal to K and sum up over all K. That's the precise thing to say. What do I get? I get the trace, right? chi alpha g,
Yes.
and chi beta g inverse. Okay? Clear? That's what I get on the left. What do I get on the right? That takes slight bit more attention. What do I get on the right? I of course get mod g by d alpha delta alpha beta. That much is clear. But what do I get on the right hand? Get clearly delta kl delta k prime l prime. Remember, we are putting k equal to k prime, l equal to l prime. That's actually delta kl squared, delta kl sum over both k and l, and k and l run over what? 1 to how many values do you have for k and k?
Dimensions.
Yeah, dimension of what? Dimension of the particular irreducible
right.
representation you're talking about. But in this case, I could just put d alpha because of course of the delta alpha beta, right? It's actually k running from 1 to d alpha, l running from 1 to d beta. But if alpha and beta are different, this is going to be 0 anyway. Tell me, what is the sum? What is this sum? How much is this? This is the easy sum, right? Delta KL square. What is delta KL square, by the way? Forget the sum. How much is delta KL square? Even without a sum. Come on.
Delta KL.
This is delta KL. Right. Delta KL square is just delta KL.
And
Then you are summing up over both K and L. What is that going to give you?
D alpha.
D alpha or D alpha square? Which one? It's going to give you D alpha.
Yeah, it
right.
should be alpha.
Gives you D alpha. So this is your extremely simple result. No indices left any longer. If you take all the characters of every group element, chi alpha g, chi beta g inverse, and sum up over all g, you are going to get this mod g delta alpha beta. Okay? Right? All the k's in the individual indices have gone away. I deliberately, okay, I had too much information so far. I had information about what happens for every k, every l, every k prime, every l prime. Just to make it easier for us and cut the clutter a bit, I've actually translated this to a statement about characters, which is a lot simpler. Which, by the way, of course, the fact that I'm reducing information here by choosing specific values of k prime and l prime, namely equal to k and equal to l, and then adding up over all k and l, makes me lose a lot of information which I had originally. It so happens that the equation that I'm getting right now is actually still powerful enough, despite losing the huge amount of information, is still powerful enough to make a lot of for us to be able to draw a lot of conclusions about irreps just from there. Okay? Yeah. However, sometimes we will have to fall back on the original GOT because after all, we have lost information getting here. So sometimes we will need some information which was there in the original Great Orthogonality Theorems. However, that's the rare situation. In most cases, most of what we are going to do in our applications will rely only on this. And that's a great simplification, right? This is a much simpler equation than the one we had before. And it in fact gets even simpler. By the way, if this happened to be a unitary representation, then what would this change to? If the representation were unitary, then chi beta g inverse would become what? What would this become? Yes?
chi star beta G.
Yeah, this becomes chi beta G.
Chi star beta
G,
G.
not G. Okay, the great thing is not G inverse, chi beta G conjugate, right?
Yeah. Yes.
In fact, the mod G is slightly embarrassing, so why not put it on this side? And then, okay, I'm now going to claim something rather drastic. I'm going to claim that this is true not only for the unitary representations, it's true for all representations, for all irreps. Not all representations. Of course, anything I say here is for irreps, but I'm claiming that this is true for all irreps. Can you see why? Yes? What I had for all irreps was this statement up here. This thing is equal to mod G delta alpha beta. Now what I did was, specifically for unitary representations, I could easily see that chi beta G inverse is chi beta G's conjugate, so I have this relationship.
Does it follow from that all representations on finite groups are equivalent to unitary representation?
Exactly. No matter what representation is started with, it may not be unitary, but it's equivalent to a unitary representation. And that means that the character, which only depends on, which is the trace of those matrices, will not change when you go over to the unitary representation, right? So no matter what irrep you have, the characters are the same, whether it's in that for that particular representation or any equivalent one, including the unitary one. For the unitary one, this is of course correct, but the characters are the same no matter which representation you're taking, which means this is true for all irreps, this statement. Okay, I don't even have to specifically. So the point is, this theorem that we proved that all representations of a group, not just of a finite group, not just the irreps, but all representations are equivalent to unitary representations, or equivalent to a unitary representation. But that theorem actually came with a construction, right? The proof of the theorem gave us a construction which allowed us to calculate the unitary representation. However, that rather lengthy construction you don't even have to ever go through with. The point is, this result will work simply because it is equivalent to, all you have to know it is that every representation, including every irreducible representation, is equivalent to a unitary representation. You don't need the actual unitary representation for this. So even if you start with a representation which is not unitary, suppose you wrote down your bunch of irreps in this list of yours, and the one which you wrote down was not a unitary representation. I don't care. It will still work. This is okay. This theorem will still work for all representations. Okay, not all representations. In any case, this theorem only works for irreps, but this is for all representations, all irreducible representations, not just unitary ones. Now, can you tell me what this looks like? The left-hand side? Quickly, what does the left-hand side look like? An expression like this.
It's like a inner product, like
it's like a dot product or inner product is actually the Hermite product for complex vector spaces. Physicists actually call that the inner product no matter what. Mathematicians usually are a bit more picky. They keep the name inner product for sigma ai bi, or more precisely, they keep the name inner product for products which are symmetric. This one is not symmetric, right? It's actually called sesquilinear. When you invert the order, it sort of conjugates. So that's what mathematicians call the Hermite product, which to them is a generalization of the inner product to complex vector spaces. Physicists usually meet the inner product most often in quantum mechanics, where it is really the Hermite product that they meet. So they usually don't bother about the distinction. They call both inner products. They just say inner product on a real space is something which is symmetric. Inner product on a complex vector space has this extra conjugation. Be that as it may, this is really an inner product in that sense. Okay. So can you tell me one thing? If you think of the geometrical language here, what is this telling me about inner product between what? Basically what you are saying is, suppose I have elements G1, G2, Gn of the matrix of a group. Remember, there is a finite group, so n of course is mod G. Then this sum, if I...
They are orthogonal.
What are orthogonal? Then if you form
All the reducible representations.
Form a vector, first of all, by taking chi alpha G1, chi alpha G2, chi alpha Gn, you form this vector, which is of course a simple row vector that I've written down with n elements. And I do it not only for the representation alpha, I also do it for the representation beta. Then these row vectors, or I could have of course written them as column vectors, except that it takes a lot of space to write column vectors. These two row vectors are orthogonal, as you say, as long as alpha and beta are different. Even I could even normalize this, right? Even make it orthonormal by just putting in a 1 by, instead of defining it this way, I can put a 1 by root mod G in front of both of them. Then the vectors will be orthonormal. Okay. Now, can anyone tell me what does this tell you about? They are orthonormal, right? Of course, fine. But what does it tell you about the number of possible irreps? When I
equal to the dimensionality, like number of elements.
no, not really. Close, but not really. By the way, number of irreps, of course, is infinite. What I'm saying is number of inequivalent irreps. So when I say number of irreps, I always mean that. Does it mean you are saying it's equal to dimensionality, right? Equal to, after all, that's the dimension of the space. The row vectors there are n element row vectors, so this is an n dimensional space, and you are saying the number of irreps is equal to the number of group elements. Is that correct? Is that what this is telling you? The orthogonality relation?
Yeah, I think so.
No, it's not. What it's telling you is this. They can be less, right? All you're saying is they're orthonormal. Nobody said they're complete. The maximum number of orthonormal vectors are, forget normality, orthogonal vectors are always independent. So the set of all such vectors, if you take them together, that will be an independent set, a linearly independent set. You cannot have more linearly independent vectors in a vector space than the dimensionality of the space. Since each irrep corresponds to one such vector, each irrep in our list of inequivalent irreps correspond to one such vector, the number of elements in our list cannot exceed the dimensionality of the group. But it doesn't say it has to be equal to, right? Come on.
Yes, sir.
In a 5-dimensional space, I can have 2 independent vectors. What I can't have is a set of 6 independent vectors, right? But I can have a set of 2 independent vectors, even 1 independent vector, or 3, or 4, or 5, right? Clear?
Yes, sir.
Actually, it's actually easy to show that it's actually less is usually true, because remember we said it's a class function, right? Character. What that means is that instead of this sum as it stands, I could write it like this. It's summing up over the entire groups, entire group, every element. I could just sum it up over the classes, and I can get something like this. Chi alpha C but then there will be one extra factor, the number of elements in the class. Just imagine if we did this for this E, A, B, C, D, F, the group S3. Then identity will have one character. A, B, C, each of them will have the same character. So you can just take any one of them, multiply that result by 3. You're adding up over all group elements, but adding up at contribution from A, contribution from B, contribution from C is just 3 times the contribution from A and 2 times the contribution from D. That's it. Just hold on. Hello. এই রে শুধু আসার কথা ব্যাপারে বলতে জানি না এখন তো খুবই ব্যস্ত থাকবে এই মুহূর্তে বোধ হয় আমি একটু পরে খোঁজ করে তোকে জানাচ্ছি আচ্ছা না আর্জেন্ট ব্যাপার নিশ্চয়ই না তাহলে আমাকে বলে হয়তো So this has to be equal to delta alpha beta. Everybody with me so far? So instead of summing up over all the group elements, could just say I will not bother with the individual group elements. I will just take one class each of the classes, take the value of the character from that class, which is the same for all the group elements belonging to the same class. Just put that in the sum. I will multiply it by the number of elements. Is that okay?
Yes.
But then can anybody now tell me what this tells us about the number of irreps? What I could do is form vectors like this.
So number of conjugacy classes.
Yeah. So instead of I could form a vector whose elements are essentially characters for a given class, except by you weight it with this factor n square root of nc1 by mod g. To do that, the number of elements in this row will not be the number of group elements because I'm taking only one element from each class. It will just be the number of classes. So what we actually have is number of irreps is less than equal to number of classes. And since the group typically has less classes than elements, most groups do except for Abelian groups. In Abelian groups, of course, every element has to sit in its own class, right? Because when you do H inverse in an Abelian group, you can always jump across the G and cancel H inverse, which means the only element which is conjugate to G is G itself. So in an Abelian group, every element sits in its own class. So for Abelian groups, the number of classes is the same as the number of groups, but in general, this is what happens. So number of irreps is actually quite limited. For the group S3, you have already shown that you cannot have more than 6 classes, right? Because there were 6 elements in the group. But now I have shown that it can't have more than 3 actually. Forget more than 6. It's actually less. Clear? So this is a huge simplification. Remember, so far we had no clue. We could have infinitely many inequivalent irreps for all I cared. At least so far as for all I knew, the number of inequivalent irreps for a given group could be infinitely many. And there are groups for which this is infinitely many. Infinite groups for which these are infinitely many. But we have actually shown a huge restriction. First, just from the orthogonality relation directly, without considering the classes, we could show that the number was limited by the size of the group, could not be more than the number of elements of the group. Actually, we have now shown that it has to be bounded by the number of classes. Cannot be more than the number of classes. Clear? Is it okay? This is a very critical thing, that you cannot have more irreps than the number of classes. Actually, I will wind up today, so I will next day we'll take on from here. But Next day, one of the first things we will show is that it's actually equal to the number of classes.
Sir, you
I've
while
heard.
doing regular representation, you I think mentioned this that the it contains all the irreducible
Yeah, but I
representations.
mentioned this. I had no proof of that, right?
Yeah,
I just mentioned that. Of course, the regular representation, I already mentioned this, you're right, but I mentioned this there without a proof. I just said the regular representation is important because as we will find, we have not yet found that. We will find next class that the regular representation has every one of the irreps. In fact, it has the irrep alpha occurring d alpha times. Exactly. What that means, of course, is that immediately puts a bound on the number of irreps you can have. But that was a statement that made then without a proof. I just said that is true. Now at least we have a proof that the number of irreps cannot be infinitely large, in fact cannot be very large. It just has to be bounded by the number of classes. The first thing that we are going to prove the next day is that it's actually equal to the number of classes. So basically these vectors over classes that we have written down, they form a complete set. That's what we need to show. It's not just a linearly independent set, they're also complete. That means they form a basis of whatever vector space we are talking about. Not the vector space V. Or there is no one vector space V here, right? All the different irreps could be over different vector spaces. But what we are saying is this vector space that we have cooked up right now with vectors whose elements come from the characters. This vector space will be shown to be spanned independently by these character vectors. And therefore, we will end up with the result that the number of irreps is exactly equal to the number of classes. So, for example, our group S3 has exactly 3 irreps. Okay, and the GOT or the character version of the GOT will be enough to actually tell you not only that, it will also tell you what the sizes are and what the characters are, by the way. You can even find out the characters without even writing down a single representation explicitly, at least for this case. So the character table for this group, which is essentially characters for all these inequality irreps, can be written down without even writing down the representations, at least in the most part. Okay, so that is what we are going to cover the next day, and then, as you will see, that all this will also tell you how many times, given a reducible representation, or let's say given any representation, how do you know it's reducible or not? Okay, remember, to prove that a representation is reducible, you have to show that all the matrices in the representation can be brought to a block diagonal form with the same block diagonal structure by a single similarity transformation done on every one of them. You happen to be lucky enough to start with such a representation so that you can see that the thing is reducible, then it's fine. But usually the representation that you will be led to, say from a physical application, you will often get a representation of a group. That representation may not turn out to be block diagonal to begin with, and it may be very, very difficult to figure out how to block diagonalize them simultaneously. Remember, you cannot do, it's not just block diagonalizing one of them. By the way, if the job was to handle only one matrix, sorry, can you just tell me why it's trivial that you can block diagonalize it? What would be the procedure to block diagonalize a particular matrix? Yes?
and just choose the basis to be the eigenvectors of the.
Yeah, so you basically diagonalize it. Every matrix, at least every unitary matrix definitely is diagonalizable. As a finite group by groups, of course, you have equivalent to the unitary matrices. So all of these for finite groups, all the representation matrices are diagonalizable. So you can diagonalize a given matrix, no problem. But what the similar transformation which diagonalizes one matrix will usually not diagonalize the other matrices, right? You don't have one matrix to talk about. You have one matrix for every one of the group elements, which is why you are not even talking of diagonalizing all of them. You can't diagonalize all of them together, usually, unless they all happen to commute and have a sort of common eigenvectors. So usually we will not be able to diagonalize them all together. The best you can do is block diagonalize all of them together, and that would be a horrible thing to do, because if you don't have any additional help from some theorem, it will be very difficult to do. So even whether a matrix representation is reducible or not is very difficult to figure out if you had to do it from the definition, from scratch, because it will be a matter of huge amount of luck to be able to find out a similar transformation which will block diagonalize all of them together. However, as we will see next day again, this orthogonality theorem that we have derived will immediately tell you whether a representation is reducible or not. In fact, you don't even need the whole matrices for that. All you need are the characters. Just the characters, that's it. Tell you whether they're reducible or not. They will tell you if it is reducible. It's not only will it tell you whether it's reducible, it will tell you how many times each irrep occurs. And if you use that specifically for the regular representation, this machinery, you will find that in the regular representation, each irrep occurs exactly d alpha times. And if that, okay, all this is of course being stated without proof. That's for the next class. But this will also give you one immediate result, that if you were to write down a given matrix in the regular representation, what will its size be? What is the size of a matrix representation in the regular representation? What is the size of any matrix in any representation? It's the dimensionality of the space, right? The representation is on a vector space. And the matrix is, of course, n by n if n is the dimensionality of the vector space. What is the dimensionality of the group algebra, which is the vector space which we use here for the regular representation? Yes?
A number of group elements.
Number of group elements, right? Because each of the group elements form a basis. That's how you set up that's how you define the group algebra to begin with, right? So what this tells you is that you get one very important result immediately, which is d alpha. Okay, let's just think about it this way. If you think of the block diagonal form which you can put regular representation matrices in, then a d alpha dimensional representation, which is d alpha by d alpha, will appear on the diagonal how many times? There is a result which I quoted right now. Of course, I will prove it the next day. It will come d alpha times, right? So a three-dimensional representation, if it's there, will occur 3 times. A 4-dimensional representation will occur 4 times. A 9-dimensional representation will occur 9 times, and so on. Okay? A 1-dimensional representation will occur only once. Another 1-dimensional representation, which could be inequivalent to this one, will occur again only once. Dimensionality does not uniquely tell you what the representation is. So there could be 2 inequivalent 3-dimensional representations. They would both occur 3 times. But what this tells you is one thing. How many rows does this make? You take all the d alpha by d alpha representations together for this particular inequivalent irrep. How many rows?
d alpha square.
D alpha square, right? Which means if you added up this up over all the irreps, this happens for all the irreps, you just get the size of this number of rows of this matrix. So pending a proof of this result that we are just quoting right now, this is a very important result actually, that the dimension of the irreps also is strongly restricted. Their squares have to add up to mod g. So for example, going back to the S3 example, how many irreps does it have? Again, Not proven. So far what we have proven is S3 has at most 3 irreps. What we have not proven but stated is that S3 has exactly 3 irreps. Okay? And the dimensionalities must obey this equal to 6. Right? Is it okay? Then what does it tell you about D1, D2, D3? One, 1, 2 is the only possibility, right? First of all, because the sum of the squares add up to 6, you can easily see that you cannot have anything more than a 2-dimensional representation. A 3-dimensional irrep is impossible. 3-dimensional representation is of course possible, but a 3-dimensional irrep is impossible. And the only possibility is 1, 1, 2, which immediately tells you that S3 has 2 1-dimensional irreps and 1 2-dimensional irrep. Okay. And if you play around with the character orthogonality relation a bit more, you can actually find out what the characters of those irreps are without much difficulty. Write down the character table. But what I wanted to do is illustrate that just these relations that we have derived today, they are powerful enough to tell you a lot of information. Here it classifies the irreps completely. Not only that, it actually with a bit more work you will find all the characters without ever even explicitly constructing a single irrep. Sometimes you have to construct irreps, at least some of them, but this cuts down the work a lot. Okay, so I will. Yeah, go ahead. Yeah, go ahead.
Confused. I mean, the D1 dimensional representation happens to be only 1 times, right?
No. D1 dimensional, every d alpha dimensional representation occurs d alpha times. That's the result. I did not prove it. That's a result which you will get. Look, next day what we are going to prove are several results. First of all, that the number of irreps is exactly equal to the number of classes. We haven't proven that yet. We have proven it's less than equal to. Then we will prove, or we will figure out a way which will tell you from the character of a representation. Remember, even irreducible representations or reducible representations, any representation is a character, right? That is, you just take the matrices of that representation, find out the traces. If you have a character of a representation, of course that means the character vector. You know the characters for every one of the classes. Then that will be enough to tell you whether the representation is reducible or not. That's again a result which I did not prove. Then another result which comes in is that it will also, it comes in before this, that it will tell you how many times a given irrep occurs in a given reducible representation. Okay. And finally, if you were to use these results on the regular representation, you will find that every irrep occurs in the regular representation. It occurs as many times as the dimensionality of the irrep. So in this case, for example, for S3, the one-dimensional representation, the first one-dimensional representation occurs once. The second one-dimensional representation occurs once. The two-dimensional representation occurs twice. Which is why, if you look at the block diagonal structure, you have a 1-by-1 block for the first one-dimensional representation occurring only once. Another 1-by-1 block, the second one-dimensional representation occurring once. And then two 2-by-2 blocks for the 2-by-2 representation, two-dimensional representation irrep occurring twice. So that's why it's once.
Regular representation.
This is only for the regular representation. Yeah. But the advantage is for the regular representation, this particular result, that every irrep, after all, look, given any, suppose I have this, for S3 I have one dimensional representation and this I already have this result, 1, 1, 2, right? All I have to do is put them together like this. Say I can put the one dimensional representation 5 times down the diagonal. And then not put the second one dimensional representation at all. And put the 2-dimensional representation maybe only once. This will give me a 7-dimensional representation, right? Is it okay with? Do you realize that you can just put the representation together to form a reducible representation? Right? Is that okay?
Yes.
So, if you're talking about arbitrary reducible representation, how many times the irreps occur in that is arbitrary. You can put the first one 5 times, the second one 21 times, the third one maybe not at all, or even 5 times or whatever. Okay. So those will be arbitrary representations of the group. But the regular representation has a very special rule. It's the one representation which guarantees that every irrep occurs exactly d alpha times. Now how do we know that? Well, we know that because the character of the regular representation is rather trivial. Can anybody remind me what that is?
0 if g not equal to and n if g equal to e.
It's 0 if g is not equal to e. So if you think of the classes, identities in a class on its own, every other class has 0 character. The identity has a class mod g. Okay. Using this result and the orthogonality theorem, you will easily be able to prove. In fact, the proof is really rather trivial. You should be able to even work it out yourself from what we have. Well, from what we have done, the only non-trivial proof left is the demonstration that the classes are complete. Okay, that's slightly non-trivial, not very difficult. But the rest of the statements that I made right now can be proven once if you assume that the classes form a complete set of independent vectors, the class vectors for the irreps. Then whatever else I have stated today, I have stated them without proof, but the proof would be rather easy to do. You should be able to figure it out yourself. Even the class result is something you should be able to figure out, but it will take a bit more effort. But that's the first result that we need in order to prove the other results, which is why I'm deferring it all to the next class. Is that okay with everybody? Do you understand the point? The point is, if I did not have to prove that the classes form a complete set of the class vectors for the character vectors for the classes form a complete set, they did not have to prove that before going on to the next results. I could have finished all of that in 15 minutes. But I will not. I will defer it for the next class because for all those proofs, I need to first prove this one result. That which is slightly more difficult to prove, not very much, but slightly more difficult to prove than the other results. The other results are, well, really trivial. They're just, now that you have a dot product of your own, it's just playing with it. And in fact, you have dot product for which these vectors are all orthonormal. The other results are simply playing with the dot product. And something which you can do at, say, class 12 level. The only non-trivial result is to show that these classes form a complete set so that every character vector can be written down in terms of a linear combination of the character vectors for the irreps. Once that's done, everything else follows. Trivially. Almost trivially at least. Okay. But since that one step is something which I will take some time to do, I am leaving it for the next step. Okay. So any further questions? Yeah, go ahead.
In the H3 example, is there any restriction on the one-dimensional representation that those two one-dimensional representation will be inequivalent or equivalent?
Have to be inequivalent. We are only counting inequivalent representations.
Okay.
Equivalent representations are not being counted. As I said, how many equivalent representations can you have? The answer is infinity in general. Not for the one-dimensional ones. For the one-dimensional ones, of course, you can have only one inequivalent one, right? Because all the one-dimensional representations definitely commute. They're just numbers, effectively. They're one by one matrices, so they're numbers, and because they're numbers, they all commute. So there's only one even equivalent representation for one-dimensional ones. But in general, all these results that we have proven are for inequivalent representations.
Okay.
So 2 1D inequivalent representations, 1 2D representation, inequivalent representation. Any other 2D representation is equivalent to this one. Or, okay, that's not really true. What's the correct statement? The correct statement is any 2D representation of S3 will either be equivalent to this particular 2D representation, which we have not stated yet, but even we have already found out, by the way. The matrix representation that we found on 2D, that's irrep that you can actually show. Or it could be a reducible representation made out of 2 copies of either the 2 irreps, 2 1D irreps, or 2 repeats of the same 1D irrep. That's the only possibility. But the 3D irrep that we found out using the homogeneous quadratic functions, at least we found out partially. That actually, okay, 3D representation, that's a 3D, it cannot, S3 cannot have a 3D irrep. That's a 3D representation, and the 3D representation is reducible. Oh, the only question is, does it have 3 copies of the same 1D irrep, or a mixture of the 2 1D irreps, 2 of one of the other, or one of the 1D irreps and a 2D irrep? That's something we can answer once we have the machinery from the next class, without having to block diagonalize the matrices, and that is the critical part. Okay, further questions? If not, let's call it a day today. We will meet again on Tuesday, right? In the meantime, try to figure out why don't you try to prove the results that I have stated. If you can't figure out the completeness part, just assume that to be true and use it to find out these results. How to prove irreducibility, how to find out the number of times an irrep occurs in a representation. As I said, all the information you need for that is already there in the orthogonality theorem. That's it. Okay. Okay, fine. So what we are going to do is we are going to call it a day today. Let's stop recording.
Sir, recording.
Yeah. Let's stop the recording. Although if everybody leaves, the recording will stop anyway. But let's not make it.